Tom Friels, Professor of Automotive Technology at Sinclair Community College in Dayton, Ohio. And we have a series of videos here to help explain and help instructors with teaching electric vehicle technology. And that has been provided thanks to an NSF grant that we were awarded recently. And if you'd like to know more, take a look at our website at selfdrivesinclair.org. A very useful test for diagnosing electric vehicle, hybrid vehicle applications is the use of a Milliohm meter. A Milliohm meter is actually a piece of equipment used for very low resistance type of measurements. So in a prior video, depending on what order you looked at these, we did a video on Milliohm meters, which is for pretty much the high side of resistance, or actually you're using the conductor to test the insulation of something. This is almost the polar opposite. So a very low resistance test is used for most of the time places like a drive motor, but there are other applications I'll show you now that are coming up now with some EV service situations. So we want to basically describe this piece of equipment, kind of give you a comparison to a normal Ohm meter and why it's so different, where it can be used on the vehicle, whether you have components like we have here on the cart, whether you go straight to a vehicle. I basically use these in our training sessions and in our class and give them some different scenarios. We actually can do a couple different faults and bugs and things like that to kind of simulate things. One of these will show up as a fault to give you, some reference on that. But some things to talk about with the meter, and we'll incorporate some close-in shots because obviously we're a little far away here. But basically, the setup to get ready to test something, how temperature definitely plays a part in this. The fact that we have actually 4 leads on this meter instead of just 2. I'll try to explain that to you, of the reason for that. We'll use, actually to help kind of explain and show how this is used. I've got some different lengths of solid wire that are handy when you're teaching this type of subject. Even in something like a basic electrical course, that's something that could come up when you're discussing like wire gauge, wire length, and show its effect. When you're just using a straight up Ohm meter, you can't really see those changes too easily. But when you get down to this level, we're talking on the milliohm scale, you can actually see a direct correlation of the different resistances when you show different lengths of this wire. That's mainly for the explanation and maybe something you can use in a lesson to help kind of reinforce how this thing works. On the on-vehicle side, you basically need to get access to anywhere there's a high voltage connection where 2 pieces basically overlap. We'll try and get you a nice zoomed in spot for that, or access to the cables for your 3-phase windings for any type of drive motor is another spot. So as far as that meter is concerned, we're basically using the Hioki model right now. Pretty common. We've seen some OEMs that basically are going with this type of meter. There are other obviously styles of this and brands. The other one we do have is more of a bench unit. Plugs into the wall, probably more for an electronics technician than an automotive technician. So this is completely portable and runs on AA, so that's why it's a little bit better and more conducive to our environment. It does have a temperature probe basically to account for that. That actually becomes a pretty important spot when you're talking about measuring resistances that are even lower than a regular Ohm meter. Any type of temperature fluctuation can affect that. So we'll give you some examples of that. So what this is for is just to automatically adjust to whatever your ambient temperature is, and it will pretty much take that into account when it gives you a reading. The leads themselves are basically alligator clamps, but the main difference of that is there actually is 4 wires involved in this, not just 2 like a typical Ohm meter would be. And the reason for that, and we'll put a graphic up to help explain that, there's actually 2 circuits in this instead of just 2 leads. Okay, so one part of that circuit powers the component that you're testing, right? So it has a constant current source. It's going to power that component. And then basically the other one comes around from the outside, so to speak, and that's taking the voltage drop of whatever that component is. So if it's a piece of wire or a connection or a winding, the leads now aren't going to affect or basically influence the resistance of what you're testing. And the reason why that's so different is on a regular Ohm meter, you have your typical two leads. So the current source and the measuring device is all using the same leads. And what happens with that, and I'll basically can use a lead as example. One lead basically has more resistance than actually some of the specs of a lot of these electric motors. So you're already, if you try to use this to basically diagnose something, the leads themselves are already a higher resistance than the component you're trying to test. So that kind of leaves this one out. It's not really something you're going to be able to use that for, just because of the low level of resistance that we're talking about. So as far as the setup for this, and we'll have a zoomed in panel for this, but we basically need to put both leads together, and they are marked. They have a triangle marked for the panel. They have another one on each one of the leads. You want to match those up, and then basically you can let the meter zero itself, and then you can do a zero adjust if you hold that button. So it's going to account for temperature. It's showing me 21.8 Celsius. When you look at some specs, really depends on OEM whether they're going to get this detailed, but they will usually give you a spec of a certain milliohm reading and account for it at, let's say, 68 degrees. Well, we can't always have our shop environment at 68, so you either do the math to adjust for it with an equation, or you have an adjustment basically built on the fact that the meter's actually taking account for that. Now, in a bench situation like we have here, these are all acclimated and been in this building for years, so they're going to be the temperature of the building. What becomes a little more challenging is if you drive a car in off the road, it's up to temperature, and most of these motor windings, if you looked at some data, are probably about the same as what coolant temp would be in an engine. So look, you're looking at 180 to 200 degrees Fahrenheit. That's quite a bit different than just measuring something off the bench. So it probably would be a good idea to let something sit and acclimate for several hours, if not overnight, before you were going to do some type of test on a live vehicle. So once I'm set up for that, now I can take a reading with that Milliohm meter, and just for example's sake, using some solid wire, I cut a bunch of these at different lengths, really just to show an example. So I got a 4-foot piece of stainless steel welding wire here, and since our Milliohm meter has such a tight tolerance and a accuracy, I've got a long piece of wire. I actually have a 1.4 ohm piece of wire, so I'm not showing anything amazing right now. But as we start to go down in length, you're going to see that this is pretty much going to go completely in half of what we started with. So here's a 4-foot piece of wire, 1.4 ohms. Two-foot piece of wire. So I cut it in half, and my reading pretty much went in half. Not on the money, but pretty close. So now I've got basically 722 milliohms, so completely half of what I just showed before. So if we keep dropping this down, now I'm down and cut it in half again. There's another half, so I have 350 milliohms. So it's kind of showing that same gauge of wire, that length, I'm going exactly in half on my length. It's going exactly chopping in half the resistance of that wire. Now we're already low enough that, you know, this is something that's going to be an accuracy problem when you're getting to, if you're using a regular ohm meter. So we go a little shorter here, break that one down in half. Now I'm at 171 milliohms. Now 171, just to give the example, just one lead off of my normal ohm meter, and I put 2 probes on each end just to get a better access to clamps here. So this is just to show the difference of, or actually the influence that a lead can have on an ohm meter. Now when you're using that in a regular automotive application, you know, let's say you're testing a fuel injector or a battery cable or anything like that, you're usually not worried on much of anything once you get below an ohm or maybe a half an ohm. But now we're talking about some items that might have specs like 6 milliohms. 6 milliohms is a few decimal points past what this regular ohm meter can read. All right, so with one lead of my typical ohm meter, and granted you have to use 2, so just for example's sake, I've got 45 milliohms on just my lead. So if I have both of those, I'm now basically on the cusp of having an entire ohm that's influencing my reading on whatever it was. Now again, for something like a fuel injector or even ignition coil, there's usually built into the spec, give or take a half an ohm, give or take an ohm, maybe even a couple ohms that's going to be within spec. And that's what's accounting for. You're using a regular ohm meter, you have different temperatures and things like that. But when we have a motor winding, let's say, a lot of these motor windings might have, for instance, the one on the table has, I believe, a 135 milliohm is the spec. So if I've already got a whole ohm, I'm blowing that out of the water with the fact that I just can't read that low. Okay, I wanted to show a example here to reinforce how temperature has a great effect on the resistance of your conductor, especially when we're talking about something that's this low of a resistance value. So I have my short piece of welding wire from earlier, and we're sitting here at about 170 milliohms now that it's stabilized after I tested out a little bit of the influence of heat. So I'm going to warm that up, and as it warms up, you'll pretty much be able to instantly see how much of effect that has. So I'm increasing my resistance pretty quickly just by warming up that wire. There's significantly amount there. All right, so we started at, was it 170? So I'm already up basically 20 milliohms just by changing the heat or changing the temperature of the conductor. All right, so I've got a couple motor windings, just this the stator. These are taken out of some transaxles from some old Gen 2 Priuses, so those are usually pretty plentiful out in the junkyards and things like that. I have one of them as my control subject here that's going to basically should pass my test, and I have one, for example, that basically has a fault in it, so you can kind of see it both ways. So 3-phase winding. I basically need to just test all different combinations of this, so I have 3 different things that's going to come up. And honestly, it doesn't matter. Most of these are pretty much described as a UVW in the wiring diagram and things like that. When it comes down to it, you're basically looking for all these different combinations to test between them, and you're looking for any fault that would be between the two. So I've got a winding here that if I had a low resistance issue, what that equates to in the vehicle is that's a huge current ramp problem, right? So if it had an even lower resistance than it's supposed to, now lots of current flow is basically going to happen. A lot of current flow makes a lot of heat. That's going to be something that the system, no matter what type of vehicle, is going to pretty much try and protect that, show that as a fault, and shut that circuit down. So 135 is basically the highest part of the scale, or the highest part of the spec for this. I'm sitting at 127. Now, more importantly to this, and you probably won't find this in OEM because it's kind of sporadic between different manufacturers, and I won't mention any, but it's a little inconsistent and a little bit unclear. From attending a lot of different training over the years through different sources, SAE and some independents and some OEMs, pretty much come to the conclusion that you want this to be very common between the three, right? I want these to be as close to each other. Perfect world, I should have the same in every combination that I do. 127, 127, 127. That's a beautiful reading that you want for a good reading. In reality, if you're within basically 10% of each winding, that's tolerable, okay? Once you stray from that 10%, then you have one or two of your three windings. It's like an imbalance. You can almost equate that to like a misfire in an ICE type of situation. So what would it feel like to the driver? Well, it kind of depends on the severity. If it's a very definite fault, it's just going to basically stop the vehicle, and you're a tow-in situation. If it's kind of on the borderline of being a problem, it actually could get to where you feel a shudder as you're going down the road, or you might even throw it in neutral and feel a shake through the drivetrain, because once these start to show a low resistance between phases, then it's kind of like the magnetic pole and things are fighting itself as it starts to spin. So this one's basically the one that's going to pass. Like I said, it's like my control subject there. So that's a good example. If I switch over to its neighbor, basically the same type of component, might have been a different model year, but definitely from a Gen 2 Prius. Now we can show some issues here. Now I'm all the way down to 27.2, all right? I'm just between two legs. Let me go with another one. 24, 18. Now, they are 10% within each other, but if my target was 135, or no more than 135, this is where the judgment call comes in, because a lot of the service info is not real clear on this. If I had a circuit that operated on 135 milliohms, but now all of a sudden it's trying to operate on 18 milliohms, the current flow would be exponentially higher. So I basically have a winding that is what we probably would call shorted, right? Which it's the link. Then a couple different ways that can happen is I might be actually making contact somewhere inside this winding because of the varnish and insulation might have fatigued enough where I've actually got contact. Any type of situation like that. You could have a lot of metallic kind of material that's mixed in with the fluid from maybe many miles and things, and now that's providing a path between those two windings, or three windings in that case. To actually bug this just for class purposes, we kind of did a similar thing that we did on the Milliohm meter test. And I basically ran some of my favorite self-tapping screws until I got a failure. So we like to have failures for example, so that's basically what I did with this one. All right, for another example of a place that a Milliohm meter is starting to be used, at least I've noticed in the last couple years, is anywhere there's a connection, a high voltage connection, where let's say a conductor has lapped over onto another conductor. So practical places for that, and I've got basically kind of a hub that's in a Chevy Bolt, basically, for example, here to show you, but this could be any make or model. Think of where your contactors are, any place like that where something is basically connected with a bolted together type of place. So I've got a connection in here, and we'll give you a better zoomed in spot here eventually, but I've got a hex bolt here where I've got one contact lapping over another contact. Now, why this is so important is, and this is going to be something that's going to be even more paramount when we have systems that are just increasing their voltage. Like most of our vehicles now may be in the 400 volt capacity. That's going to double, and actually some OEMs are already at that type of architecture. So when I'm running more and more voltage, the potential for arcing just becomes that more apparent. So if you may have noticed where we're starting to get away from a removable service plug, well, that's because the service plug has just a kind of a spring-loaded type of connection, and you're relying on that spring tension to basically keep that tight. When you get to the point where you're having a lot more voltage, that's a little bit less reliable, so to speak. So there's a couple other leads that are another accessory for a Milliohm meter, and at first glance, like most stuff, they just look like a couple leads, but technically they have both of those circuits built into them. So there's a little bit of a spring-loaded pointer here that when you actually make contact, it's touching two circuits, similar to how my clamps were doing earlier. So with the two of these, you still are using the two circuits that are built into the actual Milliohm meter. So for a practical example here, I'm going to go over the top of where these two connections overlap, and also I'm going to basically manipulate the torque on that bolt and show you how much it actually can change. So we'll get on top of each one. All right, so I'm showing basically 23 milliohms. If I tighten this back down, I loosened it earlier, kind of an example of how torque would play into this. I should be able to reduce that resistance reading. Now I brought it down to 17, no, there's, yep, 17 milliohms. So just by a difference of torque on the connection has a great influence on that. Now, when you look at that number, that's extremely low, but again, if you have a high voltage connection, and now I have more than I should have of some type of voltage drop across this one connection here, and think about how that could compound with all the multiple connections you have between contactors, maybe a fuse connection, something like that, where a cable bolts into a drive unit. If I start adding up a bunch of those resistances, then that really takes a toll and can be failure points, can be points of like where heat would be produced that we don't want it to be produced, especially inside a battery pack, for example. So you're going to start to see a lot more points on the vehicle where this becomes pretty paramount. Just for an example's sake, I've seen some of these connections with the spec of 6 milliohms. So if you went just in one spot like I did with those leads, they don't want any more than 6 milliohms between that spot. This one I don't have a spec for, but I just grabbed something that was easy to see. But that's something that you will probably start to notice as these vehicles, especially when we get to more vehicles with 800 volt architecture. All right, the Milliohm meter is a piece of equipment you can basically use for very low resistance reading. Showed you a couple examples, whether it's on vehicle, whether it's components on the bench. Probably most importantly part of this is acquiring some components like this. So even if you go back to maybe a salvage yard or something like that and get your hands on a transaxle from even maybe an old Prius or something, or an IMA motor from a Honda back from the late 90s, early 2000s, mid 2000s, that might be something more cost effective. That's basically where our items came from. This hub here was off of a wrecked Chevy Bolt, so it was something that was relatively inexpensive, all things considered. Your equipment that's probably where you're going to have the most investment. You're looking at probably, it's over $1,000 for the meter. These extra leads are another separate accessory, so you've got some funds to tie up into that. But it's not just a one-trick pony necessarily anymore. It used to be, this is something we did one test on. Now, since it's trickling into other components on the car, it's definitely something I can see being more utilized probably more often in teaching with EVs, hybrids. But then, even something to introduce into your basic electrical with the example of the welding wire, showing your different resistances is definitely something that's useful for that. But anyway, I believe you're gonna see more applications of this here going forward, and just wanted to share some places where we use it in our program. Thanks for watching our video. If you'd like to find out some more, check out our website at selfdrivesinclair.org, and also check out below for more resources regarding parts, equipment, and teaching methods.